good morning. I hope you had a nice weekend, and let me remind you that we dedicated a large part of our previous lecture to the examination of the third order correction to the energy, or correlation energy. And we also discussed the concept of time versions of diagrams. We discussed time versions of diagrams of the first kind and time versions of the second kind. So today we'll begin by examining the fourth order correction to the energy and in MBPT. And the reason we want to do this is that this is the lowest order correction that has the renormalization terms. Okay? Because of the use of normal ordering, we couldn't see the renormalization terms in the previous orders. By that I mean the third order, because the expectation value of the perturbation operator is 0 in our case. So we need to look at the fourth order to see if these renormalization terms are bringing some new interesting information. Also, we haven't found yet contributions from excited fermions higher than doubles. So of course, another reason to look into fourth order is to analyze, to see what kind of information we're going to find in it, okay, regarding higher order excitations. Okay, so let me start with the definition. So it is, we have a principal term that has the structure of WR0, 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 WV0, where W is our perturbation, R0 is the reduced resolvent, and then we have the renormalization term, which is Phi0, WR0, W, multiplying Phi0, W, R0 square of the resolvent, W, Phi0. Okay? As you remember, this is actually the second order correction to the energy. And this is, of course, something we expected. Okay. We know that our perturbation operator W is the sum of the one-body contribution, which we call Qn, and the two-body contribution Vn. Okay? So, as you recall, Q measures the deviation from the Piecuch regime, and V is the true, of course, pairwise interaction written here in the normal order form. And in the analysis of the fourth order, I will actually focus on the contribution from Vn. Obviously, if I replace each of these W's here by Qn plus Vn, I'll end up with multiple terms, which will have no Q's, then 1 Q, then 2 Q's, 3 Q's, up to 4 Q's, okay? But I'll focus on terms that originate from Vn only, because those are the leading terms typically, and the second obvious reason is the fact that when Phi0 is the Piecuch reference, then there are no Q is 0, and then simply all that contributes to fourth order are terms from Vn. So let me actually then write this same expression again, but this time with V's. Maybe I'll put sort of an arrow like this so that to emphasize the fact that this is not the entire fourth order, the Q is not 0. But let's have it. So this is the principal term, Vn R0, Vn R0, Vn R0, Vn, okay? Or in other words, Vn and then R0, Vn cube, minus the expectation value of Vn R0, Vn Phi0, times Phi0, Vn square of the resolvent, Vn Phi0, okay? And what we would like to do now is to evaluate both of these terms. I'll start with the principal term. And when we're done with it, we'll start analyzing the renormalization term. Okay, and its role in the entire calculation. So, to organize our work, following what we did in the third order, I'll try to group these various diagrams according to the number of lines that connect selected two vertices, okay? So we know right at the outset that if I look at the principal term, what I need to do, I have to start by drawing 4 Vn vertices, 1, 2, 3, 4. As we've learned, we do not have to worry about drawing resultant diagrams because those are taken care of by our denominator convention. Okay, and we need to come up with all non-equivalent resulting diagrams that have no external lines and that do not contain dangerous denominators. In other words, there always must be some lines between the neighboring perturbation vertices, okay? To see through all of this, you can imagine it's not an easy work, obviously. I will sort of draw these 4 vertices in a sort of trapezoidal shape, okay? So that we can easily see how the various lines go. As you will see, there's a this will benefit us greatly, okay? And I will call these 4 vertices, which I'm reading from left to right. I'll label them as vertices 1, 2, 3, and 4. And I will be organizing our diagrams according to the number of lines connecting 1 and 2. Okay? So we'll be looking at the number of lines, we'll be sort of grouping our diagrams according to the number of lines between vertices 1 and 2. And within each category of this type, that is after fixing the number of lines between 1 and 2, okay, I'll be then looking at the remaining lines at 1, and I'll be trying to see, how do they distribute among, how do they go, how many of them go to 4 and how many of them go to 3. Okay, so we'll have, of course, sort of subclasses within each bigger category, okay, defined by the number of lines between 1 and 2. Okay, well, so let's do it. Okay, this is how I'm going to set up the problem, and let's not do it. So, okay, let's start with the category where we have 0 lines between vertices 1 and 2. Well, 0 means no lines, simply. Okay? So, I'm going to, let's try to make it big enough. I'm going to draw our trapezoidal shape. All right? And no lines means that I'm, if this is 1, and if this is 2, and if this is 3, and this is 4, that means that I'm not going to have any lines going here. So I have now 4 lines at 1 that have to go either into 4 or into 3. Okay? So I'll start with the, I guess, most obvious way of drawing this, namely, send all 4 lines toward 4. Okay? That's my starting point, place, and I will call this, to sort of have some sort of organization here, I will label this diagram writing 4 plus 0. 4 plus 0 means that there are 4 lines going from connecting 1 and 4. Okay? And 0 means there are no lines connecting 1 and 3 within this category. Number of lines connecting 1 and 3. Okay? So, if I have, within sort of this notation, I would have other cases belonging to the same big category, that there are no lines between 1 and 2. I can have 3 lines going here, and 1 line going to 3, okay? According to this notation, I'm going to call this 3 plus 1, meaning 3 lines go from 1 to 4, and 1 line goes from 1 to 3, okay? Then I will have the next case where I have 4 lines here, so I'm going to send 2 of them to 4, and the other 2, okay, to 3. Then I will also have, maybe I'll finish it off here. So this will be called then 2 plus 2. Okay? 2 going into 4, 2 going into 3. Then I will have a case where we have one line connecting 1 and 4, and 3 of them going to 3. Okay? So that's going to be according to our notation 1 plus 3. Okay? Meaning we're connecting 1 and 4 with one line, and we're connecting 1 and 3 versus 1 and 3 with 3 lines. And the final case, as you can imagine, is the one that is left over, is connect diagrams. Do not use any lines to connect 1 and 4, okay? But use all 4 lines that we have and 1 to send them to vertex 3, okay? Something like this, okay? So that will be according to our notation 0 plus 4. Okay. Well, now, that we have all this category worked out, all we need to do is to simply fill the blanks. Okay, so, remember at each vertex we have 4 lines. Okay, and that means that here I will have 4 lines drawn this way. Here I will have 3 lines and 1 here. Okay, here we'll have 2 lines and 2 lines. Okay, here we'll have, put it a little bit further away, 1 line going here and 3 going here. Okay, and then the last one will look like this. Okay, we have vertices 1 and 3 as well as 2 and 4 connected with 4 lines. Okay. Of course, we know, maybe I'll use a different color now, that this is MBPT, which means that we also have reduced resolvents. Okay, I'll come back to the issue of reduced resolvent, but let's sort of at least slice the lines accordingly. And so that we can see where the perturbative denominators are. Okay, all right, that's the first class. Well then, maybe I'll put it out. Actually, Nicole, if you could show this. Okay, that's the first class. And I will now, if you don't mind, I'll erase this because I'll need more space to draw all these diagrams. Okay, is that okay if I erase the formulas for the fourth order? Okay. And I also erase this. We already know our convention. Okay, so let's just use this blackboard to analyze the next category. Well, what is the next category? Next category, according to our classification, will be the category of diagrams where we have one line between vertices 1 and 2. Okay? Exactly one line. So once again, I'll start with our sort of trapezoidal arrangement of the 4V vertices. Okay, as a reminder, this is 1, this is 2, this is 3, this is 4. And this case will be characterized by drawing exactly one line between 1 and 2. There will be now 3 lines left here, which means that we have a few diagrams within this class. Okay? Let me try to see if I have all of this in a single row. Okay, so we have 1 here, 1 here, and 1 here. And now what I need to do, I need to use the remaining 3 lines at 1 and connect them to 4 and 3. Okay? So we will begin with the case where 3 lines go that we have at 1 go to 4. This case will be called 3 plus 0. I'm still following our convention. The first number tells you what is the number of lines connecting 1 and 4. The second number tells you how many lines are used to connect 1 and 3 within this category. Then we'll have 2 lines here and 1 line going to 3. Okay, that's going to be 2 plus 1. in our notation. Okay, then we'll have, we will distribute our lines in, by sending one line from 1 to 4, and by then sending 2 lines from 1 into 3. Okay, that's going to be the case for 1 plus 2. And the final case will be to use all 3 lines at 1 to connect them to 3. Okay, to connect 1 and 3. Okay, all right. So this is going to be the picture that emerges. Okay. And again, what you need to do, so I should also say that this case is case 0 lines between 1 and 4 and 3 lines between 1 and 3. And you don't have to fill the blanks. Okay, so we'll have 3 lines here, 1 line there. Okay, because we always have to have 4 lines at a given vertex, the vertex. Then here we'll have 1 line, 2 lines, and 1 line, okay? Then we'll have 1 line here, 1 line here, and 2 lines here, okay? And we'll have 1 line here, and 3 lines here, okay? Okay, this is all we have, and maybe once again, as a sort of a reminder, I'll draw these lines, reminding us about the resultant. So we're slicing these lines here between 1 and 2, these lines here between 2 and 3, and these lines here between 3 and 4. Okay, those are the 3 resultants that we have in our expression. And I do exactly the same for the remaining diagrams in this case. Okay, well, then we'll go to our next category, which means 2 lines between vertices 1 and 2, okay? So so we'll have, again, we'll start with our trapezoidal arrangement, vertices 1, 2, 3, and 4. And what I'm saying now is I want to have exactly 2 lines connecting 1 and 2, okay? That means that I have 2 lines left at 1, and I have to send them to 4 or 3, okay? Well, there will be 3 sub-cases here, so let's draw them. Okay, so in each case we have 2 lines, exactly 2 lines between 1 and 2, and now I have to simply use the remaining lines at 1 to distribute in between 4 and 3. So the first case will be, let's use both lines at 1 and send them to 4. Okay, according to our notation, I'm going to call it 2 plus 0. 2 lines going to 4, no lines going to 3. Then I'll have 1 line connecting 1 and 4, and 1 line connecting 1 and 3. Then I'll have both lines left at 1 going to 3. Okay, vertex 3. Okay, and once again, what that needs to be done, we need to fill the lines. So we end up with 2 lines here, 2 lines here. We'll end up with 2 lines here, 1 line here, and 1 line here. I sort of missed. Then we'll have 2 lines here and 2 lines here. Okay. And once again, let's add the lines representing resolvents. So here between 1 and 2, between 2 and 3, and 3 and 4, and the same 3 resolvents placed where they are. So which you need to have to read the denominators. And then the next class, okay, from Nicole going here, is the class where we have 3 lines between 1 and 2. Okay, so once again, I think you already sort of you can see already how we do this. Okay, so we have this trapezoidal shape, 1, 2, 3, and 4. And since I'm saying I want to have exactly 3 lines between 1 and 2. I'll draw them. And as you can see, well, here there isn't much to do. You just have one line left at 1, which you can send to 4 or to 3. So it will be 2 cases in this category. Okay? So I'm going to have 3 lines between 1 and 2, and then 1 line going here, and 1 line going there. Okay? So this would be the case which we call 1 plus 0, and this will be the case which we call 0 plus 1. Because maybe I'll go back here for a second. So, let's actually complete the notation here just to make sure, although it's not probably that critical all the time. But anyway, here we have 2 plus 0, here we would have 1 plus 1, and here we would have 0 plus 2. Okay? So going back to this blackboard, those are the 2 cases that we have. And once again, I need to just fill the blanks. So I have 1 line here and 3 here. And I have then 3 lines here and 1 line here. Okay? And then, if you want to sort of consider logically all possibilities, the last possibility that we will have to consider is 4 lines, because remember, each vertex has 4 lines. So I have 4 lines at 1, so I will have to logically look at 4 lines between vertices 1 and 2. Well, let's try that. So this is our trapezoidal shape, and if there are 4 lines connecting 1 and 2, then you would have to connect 3 and 4, okay, with 4 lines, okay? But then you would end up with a dangerous denominator, okay? Here, there will be no lines. That means that this case is forbidden. It would be okay if you just consider the product of 4 V operators, but we have resolvents. So we cannot have a situation where there are no lines between neighboring vertices, okay? So we're not going to worry about that at all. Well, that's good. Going back to the previous case, maybe I also add the resolvents. And now we would like to understand what we produced, okay? Of course, the next stage in terms of computation would be to add arrows. That is very straightforward, so I'm not going to do this. So I'd like to focus on other aspects. But if you just want to try yourself, it's very easy. You can just, for example, pick up a diagram, put one arrow this way, and you will see that all the other arrows will set up. Or put it this way, so make it a hole, make it a particle, and you already have this diagram will produce 2. Okay? So in the same way, just picking up the line, okay, you can sort of figure what cases emerge. All right? Or sometimes 2. You pick up 2 here, for example, hole, particle, 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 hole. Okay? So this one will lead to a few, and so on. So, in this case, you can analyze all of them. I encourage you to try, actually. It's not a bad exercise, just to sort of make sure that you sort of, practice and practice and practice, okay? I would like here to discuss some other things. So let's begin by looking at all these diagrams. And Nicole, can we see now all blackboards? Oh, yeah, okay, because I will be looking at the whole thing. So if you look at this sort of, all these diagrams, coming from the principal term, remember all of this is principal term, okay? Well, this is the first time we see something we haven't seen before. That is, we have a lot of connected diagrams, okay? And of course, we had them in the previous orders, but we didn't have this connected diagram in previous orders. We have one here, and we have one here, okay? So this is the first time we actually have to deal with a new situation of disconnected diagrams in the energy. So let me actually then number these diagrams. I'll go through all of them. Let's call this one 1, okay? Let's call, let's see, okay, let's use this 2, and then 3, and then 4, and then 5. I will sort of use some sort of a summary, Okay, so this is, so the first 5 are here, in the category where there are no lines between 1 and 2. Then here, let's call them, let's see, make sure that it's the same notation. Yes, so this would be then 6, this would be 7, this would be 8, this would be 9, okay? Then in the third category we have diagrams 10, 11, and 12. I should say skeletons, because each one of them can have one or more, in some case, diagrams with various orientations of lines. And then here we have 13 and 14. Okay? There are 14 skeletons, and of course, more diagrams. As I said, we have two diagrams here which are disconnected. Let's sort of try to write it up somewhere. So we can conclude now that diagrams 2 through 4 and then 6 through 14, they are connected. Okay? I will label connected diagrams with capital C. There are two diagrams also in our analysis, namely 1 and 5, which are disconnected. Okay? I'm going to use DC for disconnected. Okay? Let's maybe, because since these are new to us, let's sort of redraw them here. What are these disconnected diagrams? The first one has the following shape. Okay? Okay, so we have this sort of situation. And then there are the next one, it is written, if you really look at it, the second one, the number 5, it is a little bit scrambled, but in reality, if you unscramble it, we can always move these vertices up and down, okay, to draw it nicely. The second one is really a situation where you have 4 lines connecting vertices 1 and 3, and 4 lines connecting vertices 2 and 4, okay? So then the denominators go this way, okay? Those are our disconnected diagrams. Something we haven't seen before, and we definitely need to analyze this, okay? Another thing I would like to talk about before I do the analysis of the disconnected diagrams with the renormalization terms is to, well, if you really look closely, and again, because I will now, this is going to be a little bit involving because I have to go through several blackboards. Okay, so let's also look at the types of resolvents that we have. If you look at this picture, we have 4 lines here. That's a two-body resolvent. Okay, so let's me actually mark it here perhaps. R0, 2. Then here we're slicing 4 lines. We're slicing here 8 lines, okay? That's the resolvent R0, 4, okay, 4-body one. And then here we're again slicing 2, so that's R0, 2, okay? Well, this one is disconnected, so we can see we have a disconnected diagram which has an intermediate resolvent, 4-body resolvent, and that's already on the other blackboard, okay? We'll talk about it a little bit, about this diagram a little bit later, okay? But what I want to emphasize is that this whole category, because this is the way we organize our work, because of the way we organize our work, all the remaining diagrams, 2 through 5, okay, also have the same structure. 2-body resolvent, 4-body resolvent, and 2-body resolvent, okay? And you can see all of them, they have the same sort of content. So if I go back here to this blackboard, let's actually start summarizing what we see here. We see that, and I will focus now on the connected diagrams, okay? For the connected diagrams from the principal term, maybe I should say from the principal term, okay? Diagrams 2 through 4 have the intermediate 4-body resolvent, which of course means quadruples, because you remember the 4-body resolvent has quadruplets and determinants in it. Okay, so it seems like these diagrams, the connected diagrams, of course the disconnected one too, but as I said, I will talk about it separate. We'll see if it survives. Okay, but the remaining ones, 2 through 4, okay, maybe I'll put it back. They have the diagrams 2 to 4 have an intermediate quadruply excited resolvent. Okay, so we have R04 here, R04 here, and R04 here. Okay, if you look at the next group, okay, you start with the two-body resolvent, then the one in the middle is actually three-body. Okay? And if you look at all diagrams in this group, they all have the same structure. Okay, so diagrams 6 through 9, they have an intermediate three-body resolvent, well, meaning triples. Triplex are determinants in it. Okay? If you look at the next category, where we have two lines between vertices 1 and 2, we have two-body resolvent between 1 and 2, we have two-body resolvent between 2 and 3, and we have a two-body resolvent between 3 and 4. Well, so we only have three-body resolvents, and as you can see, that means that I can say that diagrams 10 through 12, what is this? Have all an intermediate two-body resolvent, meaning doubles. Okay? And if you continue along the same lines, then this group has, maybe I'll move it down so we can record this. We have here a two-body resolvent. We have a one-body resolvent here, and we have a two-body resolvent here. Okay? And that's the same applies to the other diagram in this category, meaning that diagrams 13, connected diagrams 13 and 14, okay, they have an intermediate one-body resolvent. But an intermediate one-body resolvent has singly excited determinants, so those are singles in our lingo. Okay? So we are learning now that fourth order brings information about singles, doubles, triples, and quadruples. Okay? The question is, are we surprised by this at all? Well, no, we're not. Remember, I did a similar analysis in the third order, so let's actually sort of repeat it here. Okay? Oh, hopefully I can squeeze it. What do we have in the principal term? We have in it phi 0. We are talking about the principal term out of two-body vertex Vn. So then we have Vn resolvent, Vn resolvent, Vn resolvent, Vn phi 0. Okay? That's what we are dealing with. If you now think about it, this is phi 0. We have 4 lines here. So you have to use a two-body resolvent in this place. So I'm going to write 2 right here. Okay? Meaning that what we have here in the middle, I mean in this sort of the first place where resolvent is, we have intermediate doubles over there. Okay? And of course there's a denominator. I'm not going to write denominators. I'm just going to focus on what kinds of determinants we have there. If you read this from the right-hand side, you can see that again, by a same argument, we must have a two-body resolvent here. Okay, because you cannot couple higher than double excitations to phi 0 via a two-body vertex. Okay, well, which means that here, if I sort of try to sketch it, we have doubly excited determinants as part of our resolvent. Okay, so I wrote here phi k LCD as a branded cat because that's what we have in the resolvent. Okay. So then the question is, what do we have exactly in the middle? That's what I mean by the intermediate resolvent, the one between vertices 2 and 3 in all diagrams. Okay? You can see that if I am at doubles, I cannot go higher, so I will have, of course, some n-body components here. The question is, what n-body components? Okay? Well, you know, if you have doubles here, V is two-body, you cannot go higher than quadruples. Okay? Because from doubles you cannot go higher to quadruples because your vertex V is two-body. So I know that n is restricted. Okay? So if I start writing what is the summation over n, okay, we certainly going to be summing up to 4. Okay? And of course we can go as little as n equal 1. Because we can also go down. That's obvious. Okay? Of course, we cannot go to n equals 0. There's no zero body part of the resolvent. So that is telling you that by this very simple analysis, that this is not entirely, this is not surprising at all, right? That fourth order correction energy has, when you look at the sort of this middle resolvent, it must have 1, 2, 3, and 4 body of it. No 5 body, no 6 body. So if you are interested in knowing how important sextuples are, or hextuples, some people say this, some people say that, okay? I think it should be hextuples actually, alright? Well then, you cannot find them here, okay? If they happen to be of some importance to your calculation, you must go beyond fourth order, okay? But definitely we've learned that fourth order brings already a lot more than third or second order. We are learning about singles, doubles, triples, and quadruples. Not all quadruples, because if you look at what our quadruples are, okay, there may be more quadruples beyond, of course, fourth order, but we definitely have already the first indication of having quadruples. They are, as you will learn later, they are so-called disconnected quadruples in the Kappa-Craftsman theory sense. We have triples, okay, and then we have some update on the doubles, and we have singles, which are either the update, if Q is not 0, or which are appearing for the first time, if Q is 0. Okay? So if you use Hartree-Fock theory, so in other words, we can say this. Fourth order is the lowest order which brings triples and quadruples for a pairwise interaction in the Hamiltonian. Okay? Previous orders don't have it. Don't have those two. It provides an update on the doubles, but we see doubles in the third and second order. So that's just an improvement. Okay? And it is also the lowest order that brings singles if we use Hartree-Fock reference. Okay? Or of course the update of the singles if we have a non-Hartree-Fock reference. Although those singles will be more important typically than the ones that originate from the Q operators, because Q is just a deviation from the Hartree-Fock regime, and typically we don't deviate from it too much. Although I don't want to say all the time, because we can also do differently. Okay, so that's physics of the fourth order. I want to go back now that we're done with physics of it, I'd like to go back to these disconnected diagrams, because we haven't seen them before. Okay? And I would like to also look at the renormalization terms. So, what I'll do now is the following. I will start erasing some of these blackboards, okay? Because I'll be focusing now on what is left over. First of all, I would like to analyze, is there something special about the disconnected diagrams? Okay? And I will also try to see how do they behave relative to the renormalization terms. So maybe here, I'll just remind you what the renormalization terms were. They were, here, I'll write them here. We had minus, you remember, they come with a minus in this case. We had, and we're talking about W being represented by Vn, so we had Vn R0, Vn R0, sorry, too much. Vn R0, Vn T0 times T0 Vn R0 squared Vn. Okay, those are the renormalization terms, and we have to look at the diagrams that represent them. Okay? So maybe I can do this. Let me then start, let's see. Okay, I think I'll have to start reading from this blackboard here. Okay? So did you copy all this? Okay, so I will now erase this. And let's just say a little bit about the renormalization terms. So, in renormalization, when you look at the renormalization terms, in terms of the diagrams that represent them, they are very straightforward. You have a product of a term which is obtained by connecting two V vertices, okay, with lines. You have to close them up because you have T zeros on both sides. But here, what is important is that we are coming with the resolvent in the first power. And then we have a second part of the renormalization term, which is also an expectation value. So we connect two V vertices with lines completely. But the resolvent, what you see there, is squared. Okay? And this comes with a minus. So that's how renormalization diagrams look like. Of course, you can put arrows in there very easily. Okay? So now, we have all the principal terms, we have renormalization terms, and what we already are learning is, maybe I'll write it here, is that the structure of the fourth order correction to the energy is, we have, okay, I'll write it with the W, okay, but we are learning already that we have connected diagrams. There's a lot of them, okay, there are a lot of them, okay, coming from the principal term. So I will be using this notation that when I put operators between curly brackets, and then I put a C at these brackets, I mean all connected diagrams from what's inside the brackets. Okay, remember this is going to be critical. Then we've learned that we also have disconnected diagrams. We found two of them coming, two skeletons coming out of the V, and there will be more if you start using Q's. Okay, so we have W, R0, W cube. So that's the principal term and the disconnected diagrams. And then, of course, we have renormalization terms. So I'll write it one more time so that we can see the structure of fourth order as we know it at this point. Okay? So we've learned that we have connected and disconnected diagrams originating from the principal term, and we have the renormalization term coming with a negative sign. Okay? So let's now analyze these disconnected diagrams with a little bit, with some details. Okay, so I'll put this up. I'll start erasing this bunch here. Okay. Well, you see those disconnected diagrams, Nicole? I will go for a second here. I'll redraw them though. We have them here. First of all, I would like you to realize that they are actually related. They are actually related by time versions. And not some time versions, they are related by the time versions of the first kind. Because if you put arrows in these diagrams, you don't have to change the directions of the arrows if you want to simply go from one diagram to another by permuting the V vertices. Okay? So we are talking here about two diagrams which are related by time versions of the first kind. Okay? If you don't mind, I'll use a sort of a silly symbol for this. TV1. I know it sounds like a TV channel of some kind, okay? But I don't want to write time versions of the first kind each time I talk about it, okay? So TV1 from now on, if you see that symbol, stands for time versions of the first kind. What is also interesting, I would like you to now really register this. This is extremely important. Those are all time versions that we have from one of these two diagrams. Why do I say so? Because if you try to just play with, just to permute vertices, there is a third version, of course. You can come up with one more, okay? What would that one more be? You would have to take, say, this and move it right here. That would be the third possibility. If I really want to just look at this whole problem topologically and say, okay, let's consider all possible permutations of these V vertices along the time axis. Okay, you would end up with this picture. Okay, so in principle, if I don't pay attention to denominators, I have three time versions. If I just focus on permutations, but this is not allowed. Okay, because we do not have anything here. And we need lines there. So this is not allowed, meaning that those are all allowed, all time versions allowed by MBPT. Okay, so please remember that in energy, and as you will see, this is not an accident. In energy, the disconnected diagrams in energy, in the principal term, group themselves according to time versions of the first kind, not second kind, first kind. We'll use them later. Okay, so going back then to this blackboard, let's then analyze them. So I'm going to draw them one more time, but this time I will really calculate them. So that's the first diagram, okay? And this is the second one. Okay? Alright? I'm going to put arrows in them. And I will even label these lines. How about that? So we have A, I, B, J here. And here I will have C, K, D, L. And I'll use exactly the same symbols in this one. So we have A, I, B, J. And we have C, K, D, L. Okay? And I will also put the resolvent. So we have one resolvent passing through here between vertices 1 and 2. Then we have one passing through between 2 and 3, and then one passing here. And there's one here, one here, one here. I will also emphasize that they all come in the first power. Because remember, those are disconnected diagrams originating from the principal term, and in the principal term, resolvents are always in the first power. Okay? So as you can see, these are very similar diagrams when you look at sort of the numerator part of them. They have the same weights, because you know, the weight is here 1 over 4 for this one, 1 over 4 for this one, so it's 1 over 16, and the same applies to the second diagram, so they don't differ. They have the same sign factor, because if you expand in the Brundle diagrams, okay, they will have the same sign. They have actually the same matrix elements in the numerator, because matrix elements will be products of matrix elements and anti-symmetrized matrix elements of this, and this. They look the same on both sides with the notation we applied. So you can see the numerator part is the same. So where's the difference between them? In the denominators. Okay, you can see that those denominators here, you know, are different, but I want to emphasize the fact that the denominators originate either from lines of the bottom piece, the lines of the top piece, or the lines of the both pieces. Okay? So I think it is worth now interesting notation where I will simply, when I write A, sort of A like this, by that I will mean the denominator, the part of the denominator that originates from lines of the top vertex. Sorry, top part. You know, disconnected diagram. Okay? When I say B, or write B, by this I mean the denominator, or part of the denominator that originates from lines of the bottom part, bottom piece. So it's A, epsilon K minus epsilon C plus epsilon L minus epsilon D. Okay? And as you can see, in building denominators, I have to use these two pieces, A and B. So let's also use introduce the notation where N will stand for the numerator part of our diagram. Okay, we already learned that the numerators are the same in both places because the matrix elements, signs, and weights are the same. So now let's then calculate. So what is this diagram in this notation? It's the numerator, which is the product of weight, sign, and matrix elements of the V, over the denominator, which consists of, first we are slicing lines of the bottom piece, that's the B. Then we are slicing lines of both pieces, that's A plus B. And then we are slicing lines of this piece, that's an A. Sorry, that's a BA. Okay, of course you then have to sum it over A, B, C, D, I, J, K, L. I'm not going to do this, that's obvious. Okay, doesn't contribute anything to this discussion. What about this diagram? It is a numerator, which is the same as in the previous case, divided by the following denominators. We're slicing lines of the top piece, we call this part of the denominator A. Then we are slicing both pieces, that's A plus B. You can see when you add A plus B, you end up with this denominator here. And then we are slicing lines of the bottom part, which is that denominator is called B. Well, let's add this up. Okay? Well, this is, you can see that these two expressions have something in common. They have A plus B in common. A plus B times B in common. So what we end up with is A plus B, B. And what do I left with? It's going to be 1 over B plus 1 over A. I will write it in another way as 1 over A over 1 plus 1 over B. What is 1 over A plus 1 over B? Well, that's simply, if I'll continue, if I continue here, this is N over A plus B times B. If I find the common denominator, which is AB, in the numerator I'll have A plus B. But you see, A plus B cancel out, and I end up with N over AB squared. So I managed to replace two diagrams but a single expression which has a factorized form of the denominator. Instead of these long denominators, a plus b times, okay, I factored them out, factorized this whole expression, I obtain ab squared. Well, what is the meaning then of this expression? Well, you know, remember, a means denominator of the top piece, b means denominator of the bottom piece. Numerator is just the product of matrix elements. So what we have here, we end up with, there you go, use this blackboard still. Okay? Maybe, or maybe not. Maybe I'll leave this one for the future. Let's go here. I'll go here and erase the remaining part of our analysis beginning of this class. And let's then summarize what we produced. We demonstrated now that if I add our disconnected diagrams, with the resolvents, as I said before, okay, we end up with a product of a diagram which has a denominator coming only from the A part, okay, and because A is in the first power, that means the resolvent in the first power, times a diagram which has the denominator of the B squared type. But B squared is squaring the denominator of the bottom piece. Okay? That means the square of the resolvent between the two vertices. Well, if you really look carefully at this, this is a negative of the renormalization term. So we need to see now all the blackboards. What you see here is the negative of what originates from the renormalization terms. See this? Well, this will cancel out then. The disconnected contribution to the principal term will wipe out the renormalization terms altogether, and that's a mathematical statement, not some approximation. Okay? So now, well, let's then conclude this analysis by making a huge discovery. Of course, it's an old discovery. We are just rediscovering. All right. Okay? So we started by noticing that our diagrams in fourth order can be organized into connected parts and disconnected parts, or disconnected diagrams, okay? I forgot to go easy. Just make sure, yeah? So we have connected diagrams from the principal term and disconnected diagrams. Then we also have diagrams coming from the renormalization terms, okay? And we just demonstrated that the disconnected diagrams of the principal term, those two, when added together, cancel out completely the renormalization terms. And we just end up then with the connected diagrams of the principal term. Okay? Well, this is an amazing discovery, because this really is the first manifestation of the linked cluster theorem. Okay? As you will see, as we continue this class, the same cancellation happens in every other order. We couldn't see this cancellation in the lower orders because there were no renormalization terms, nothing to cancel. There were no disconnected diagrams either. Nothing really to worry about. Okay? But now, we have, in the first case we have disconnected diagrams, and it happens that they cancel out. Okay? So, as you will see, and this is what we'll prove, if you look at the correction to the energy in any order, all the disconnected diagrams from the principal term, when you add them together, eliminate the renormalization terms altogether, and you are just left with the connected diagrams from the principal term. So principal term, as you remember, has this structure: W, R0, W to the N, and you need to just draw resulting diagrams with no external lines, avoiding dangerous denominators, and connected. Of course, connected will then immediately guarantee that. Okay? This is the consequence of the linked cluster theorem for energies. And this is extremely important because it also implies that finite order MBPT calculation leads to size extensive results. We'll talk about it later, but right now that's what it means. Okay? I want to say it right away because it's extremely important. So you're learning two things. Finite order MBPT is size extensive because it uses only connected diagrams in the energy. And, moreover, it is actually an easier theory than we thought it is. Because we don't have to worry about the normalization terms at all. All you need to do is to draw diagrams from the principal term and actually the subset of them. The subset that is the connected subset. You don't have to simply draw disconnected diagrams at all because they all cancel out. Okay? So that's the conclusion of this part. So of course now the question is there an analogous cancellation in the wave function? And if it is, what is it? Is it that we'll be somehow eliminating disconnected diagrams in the wave function or some other diagrams? Okay, we need to learn this, so let's have a little break and I'll start talking about wave function after, say, 5-minute break. Okay? Alright. Do you have any questions to this part of our considerations? Is all clear? This is extremely important. What we just did is essentially what was done by Bruckner. And then in fourth order, and then Goldstone in all orders. Okay? The famous cancellation of diagrams, renormalization terms, and disconnected diagrams in energy. Okay? So please sort of register. This is something that really made MBPT an extremely important theorem. Okay?
So are there also disconnected terms using the one body?
Yes, yeah, there will be. Yeah, so I didn't do them because I'm sort of assuming that it's enough to focus on V because V is of course the leading term and that's the only one that survives when phi 0 is not for reference. But of course you will get. They will all cancel out in there. The disconnected ones. That's the bottom line. And you can see it will be hard to discover this without diagrams. That's of course, now that you know the result, you can go back to equations written algebraic and you can say, oh yes, these two are identical, or something like this, and cancel them out, but that's not the way it was done. And I don't think, the discovery of this fact, this cancellation would occur so soon, okay, without diagrams. Diagrams are not only bookkeeping mechanisms for calculations, and certainly we benefit from them greatly in this way. As you notice, when I was doing this diagrammatic work, I organized our work. Even, I could sort of think of some, there's some intrinsic structure in them. There are time versions, for example. Okay. Last time we talked about the fact that some diagrams are particle hole partners, right? So when I talk about this conjugation, say HH with PP and so on. Okay. Some of them are self-adjoint in a way, right? So that is also interesting. Some of them, and then we know now that you can organize it according to the number of lines in the intermediate resolvent. So that tells you what kinds of excitations you have. Doubles, triples, quadruples, and so on. We're learning what kinds of excitations are in a given energy expression, and of course the same with wave function, by just counting the lines in the middle. Okay? And the grouping, as you remember, was very systematic. I just picked up two vertices and I was sort of connecting them with no 1, 2, 3, and 4 lines. Okay, and that led to this sort of underlying physics of having singles, doubles, triples, and quadruples in the so you can see diagrams really allow you to think about the expression, about the physics of the expression. Okay, really, that's an extremely important thing. But of course, what is I think particularly valuable is the fact that we have these cancellations which are mathematical. Okay, and those cancellations have now massive consequences for the way MBPT behaves. Okay, later, but if you say want to compare MBPT to CI, for example, you would see that in CI, if you take any CI configuration interaction calculation, truncated one at some level, say quadruple or some other subset of determinants, okay, you will end up with disconnected diagrams in energy. There's, you know, the only theory that, well, unless you do some special tricks, but typically the only theory that eliminates them completely is full CI. Okay? So, you know, so this CI leads to some results which are not size extensive. And that actually was a challenge in the 50s already, where people started looking at electron gas or sort of problems where the proper scaling of the energy, in terms of the scaling of the energy relative to the number of particles in a system, right, was not present in CI. Okay, we'll talk about it later a little bit, but I can already say that, you know, if you look at, for example, now some of the easiest case to look at it, and this can be worked out with pen and paper very easily. The book I gave you, quantum chemistry book by Sab also has an, I think, exercise like this. You know, if you take an ensemble of n hydrogen molecules, each hydrogen molecule is a 2-electron problem. Okay, so and you assume that they do not interact, so the Hamiltonian equals the sum of Hamiltonians of individual H2s. Then, you know, you would expect that the energy is the sum is simply n times the energy of a single H2, right? Now, Hartree-Fock energy. Suppose you split the energy into Hartree-Fock part and the correlation. Well, Hartree-Fock is size extensive. Okay. The easiest way to understand is that it has no diagrams. Right? And anyway, we drew diagrams of Hartree-Fock. You know, they were connected. I remember. So anyway, so Hartree-Fock is extensive. So if you're looking for problems, you have to look at correlation, right? And then you can prove that if you use CI with singles and doubles, you know, hoping that this is okay because H2 is a 2-electron problem, so CI with singles and doubles is the exact theory for each H2. Well, then you can show that the energy, correlation energy of the ensemble of n H2 molecules is not n times the energy of a single H2. It's going to actually behave more or less like a square root of it for large n's. Okay? And that's because these disconnected diagrams do not cancel out. Well, this connected diagram, each one of them has a scaling, but the connected diagrams have a proper scaling. So for a connected diagram, you would have n times whatever the value is for H2, right? But if you have now disconnected diagrams, say with 2 pieces, that's n for each piece. Well, that's n squared. If you have 3 pieces, right, that's n cubed. So you can see that this program, if you look at the energy, with expression that contains disconnected diagrams, you end up with various powers of n, the number of particles in an ensemble, and that will actually, you can show that this can be summed up into something that looks like a square root. Okay, wrong dependence. So this is extremely important. You know, those are not some sort of mathematical considerations, because, you know, if your dependence on the number of particles is wrong, then you'll be losing accuracy very quickly. Okay, so this is not going to be a problem for a system with few electrons, but it's going to be a problem if you have 100 of them. Okay, or even 50. It depends on what level of theory you're using, but that's what it is. So it's an extremely important thing. Okay, especially these days when obviously we're now ambitious, we're doing quantum calculations for large systems. Okay, much larger than people used to think. So these things emerge from sort of considering various model problems initially, but nowadays it's the essential part of physics or quantum chemistry. Okay. Anyway, so let me then go to the wave function. So we discovered that there is a cancellation among diagrams in energy, so we would like to understand what happens with the wave function. Okay, we already talked about first order wave function, as you remember, so I'm not going to spend a lot of time on it. This is a summary. We've learned that the first order correction to the wave function consists of 2 pieces, the piece originating from Qn and the piece that originates from Vn, which diagrammatically are represented by these 2 diagrams, the denominators in the first power. Okay, that's fine. Okay, that's what we proved. So we have singles and doubles, singles only when you're using a non-Hartree-Fock reference. So let's look at the second order. If you look, certainly there's not much that can happen in the first order. There are no renormalization terms in it. You only have connected diagrams. So far we see that we have to go to the next orders to see something interesting can happen in them. So let's look at the second order. So the second order is R0 W squared phi 0. Okay. Once again, I will focus on the case where on the case of diagrams originating from the Vn part of the perturbation. Okay. The Qn you can do yourself if you like. It's not essential for what I want to discuss. Okay. So we'll be looking at the term which is R0 Vn squared acting on phi 0. Okay? First of all, please note that there are no renormalization terms here either because of our normal ordering. So I guess we already know the answer, right? Probably nothing will cancel out. Okay? Because it seems like the renormalization terms are the ones that should be eliminated and we don't have them. So they will not be cancelled out probably because there are no terms like this. However, let's look at this for two reasons. One of them is your homework, problem number 1. The second one is maybe we're going to learn about what kinds of diagrams can cancel out. Okay, so we have 2 V vertices. Okay, I will not solve the whole homework for you, but I'll give you at least the beginning. We have 2 V vertices and you have to form a product. We have to form an expression, diagrams with external lines. Remember the MBPT rules. Diagrams with external lines, avoiding dangerous denominators, okay? Okay, with lines extending to the left. Okay, that's what we need to do. So if you think about it logically, you can only have the following cases. You can have a situation where both V vertices are kept disconnected. Okay, as long as lines are extending to the left, I'm fine, okay? I'm not violating the denominator convention because I have lines I have lines here, external lines, and I have lines between the D vertices. Then we'll have diagrams that let's start connecting them now. So we can connect the 2 vertices with one line. Okay? Maybe I'll come back to this. Then we'll have a situation where we connect 2 vertices with 2 lines. Then we'll have a situation where we connect the 2 vertices with 3 lines. And then, of course, in principle, it would be tempting to draw the next one, which would be trying to connect the 2 vertices with 4 lines. But you can do it because that violates 2 rules, actually, at the same time. First of all, we do not have external lines. And number 2, where denominator rule, here, is violated because we have no lines here. We should. Okay, so this is a no-go. Okay, so those are the 3 categories of skeletons that we have. I'm going to go back now to this category. Well, this one is easy. Actually, you're going to put arrows. There isn't much to do here. Okay, and I'm going to label these lines as A, I, B, J, and then here C, K, D, and L. Okay? I, J, K, L for particles. Okay? A, B, C, D for whole. So, sorry, what did I say? A, B, C, D for particle lines. Okay, I, J, K, L for whole lines. Okay? Alright, let's go to the next one. Well, here, if you think about it, there are 2 possibilities. This line here can be a whole or a particle. Okay? So let's do this. So let's assume first that it's a particle. And then the second possibility will be it's a whole. Maybe again I'll use color to emphasize how I start. Okay? Because you have to start the same way. Okay. Then we have to use the next lines. We have to add the remaining arrows. So we can see that let's say I'll do it here. Okay, we can have one line coming in, one line leaving, and then you can see that 2 lines are coming in, so 2 lines have to be leaving. Okay, and here we'll have 1 line in, 1 line out. Okay, again 2 lines are leaving, so 2 have to come in. Okay, and now we have to label them. And now please pay attention to the way I'm going to do this. For external lines, I will use the lowest allowed letters in a given category. A, B, C, D, I, J, K, L. And I want you to do this in your homework. Because that's the proper way, the sort of way that leads to very nice formulas. Okay? So we're going to be using these letters for external lines. So, following this model, I have here A, I, Okay, here I would have B. Here I would have, then you can see I want to sort of also, please use this canonical sort of ordering. I runs into A, J, this line here, after going through, runs into B, and then K runs into C. That's what you really should be doing. Okay? Then am I going to call this one? I'm not, so we're going to use, it looks like, well, okay, what is the next letter? It's available to me, D. But, if I use D, I would sort of not follow this convention. I'm going to use the next letter, E. So we're going to be having a convention where letters E, F, or MN, so EF for particles, and MN for holes, are internal lines. Okay? Which are, of course, summed over, well, just like external lines in this case. Okay? So that's the convention. So if you follow the same convention, then I will have, let me now quickly redraw it. So we have here AI, here I have now J, here I have B, here I will have KC, and here this line will be a mirror image of this one, so it's going to be M. B goes with an M. Okay? So there are two diagrams. Okay? And then of course you have to slice them through the denominators, right? So remember, that's in your reading, when you do your homework, you'll have to do that. Okay? Then what about this one? Well, here we can see that we have three cases. We can have both lines being holes, those two lines here. We can have these two lines being particles. Okay? And the third case would be, in this group, would be both, the two lines connecting vertices are, well, one of them is a hole, one of them is a particle, right? So it's a hole, particle. Red. Okay? And again, we have to put the remaining arrows. So here it's easy. Two are coming in, two must be leaving, two must be coming in here. Here, if you go back to the original one, two lines must be coming in, two must be leaving, and here we have one in, one out, one in, one out. Okay? That's what it is. And now you just have to put labels. So we're going to call those two again using our convention IJ and AB. Okay? And for the external lines, for internal lines, I'm going to use MN, not CD. Okay? Let's have sort of an agreeing, because in this way you will remember which lines were internal, which were external, if you kind of split them a little bit in your symbols. Okay? So I will call this MN. So you have a path, I, N, leading as an A, J, and leading as a B. You can see how nice it is now. Alright? And this one will be A, B, and IJ. And here I'll use EF, obviously. And here we'll have A, I, B, J, and then here EM. Okay? And I'm done. And again, resolve this. Here, 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 when you start reading the expression. Of course, using random diagrams. And here, if you look at it, once again, we only have two possibilities. Depending on, I will set up one of the two external lines, for example. So, I can have one line coming in, or I can have this line leaving. Okay, if you look at the remaining lines, then, we'll have, okay, let's have these two this way, and this one, and this, okay? And then here, so you have here, you can see we have two lines coming in, and two lines leaving, this vertex, and then same happens in the next one. And then here we'll have, let's see, okay, we'll do it again, similar way. Okay, and then, let's see, so we have here, two lines are leaving this vertex, so two must be coming into it. Okay, and then now you have two lines leaving out, so two must be coming in, and we're done. Okay, now you have to put labels, so I will put here I and A. Same thing here, A and I, and for the remaining lines, and the internal ones, we'll have here E and M, and then there's another hole, that's going to be an N, and then here we'll have, say, okay, let's call this F, and let's call this E, and let's call this N, okay? All right. And I don't know if you can see this M, maybe not. There's an M here at this line, okay? And again, the result is. Okay, so I did pretty much, I started your homework, okay? So please start from here. do the Brandos, do the weights, do the signs, do the matrix elements, do the denominators, write all this up, and answer if I want to tell the questions and answer. Okay, all right. But so you can see the following. First of all, we see that the second order, in terms of the physical content, okay, it has contributions from, if you really look now at our diagrams, we have quadruples, that's what your homework will show, quadruple excited determinants, I, J, K, L, A, B, C, D, triply excited determinants, doubly excited determinants, and singly excited determinants, okay? I'm going to just write it symbolically. So we have here, in second order, we have singles, doubles, triples, so, and quadruples, okay? So I'm using these sort of quantum chemistry style acronyms, right? It's SDTQ. Okay? What is interesting though is that quadruples are not all quadruples, they are disconnected quadruples. You can clearly see that this diagram is disconnected. Okay? Well, there are also connected quadruples in MBPT, okay? We don't see them here. Okay, that's very important for couple cluster theory, in particular. Okay, what else do we see here? Well, when you look at the energy, we were hoping that somehow, in energy, disconnected diagrams cancel out. But we have a disconnected diagram there, and it doesn't seem to be cancelling out. So if there is anything that cancels out, it cannot just be a simple statement disconnected, because nothing eliminates the disconnected diagram that we have there. Okay? Is this clear to everybody? So for the wave function, we cannot just think in a very sort of, by analogy with energy. We have to go deeper into the theory to understand what then cancels out. Well, if second order doesn't tell us what cancels out, because nothing seems to be gone from it, we have to go to the next one. Okay? So we're going to go to third order.
So why is that fully connected term 0?
Sorry?
Why is the connected, or why is the term with no external lines equal to 0?
Oh, because you cannot draw it. It's a wave function. In MBPT, there is rules of you have at least one resolver in corrections.
Oh, okay.
Okay, you can do this. It's no longer some sort of an exercise we were doing before. This is now the real theory called MBPT. Okay, such a diagram is in the energy, but it's not in the wave function. Okay, because we need external lines, and we need them not because we just said so. We need them because we have this leftmost resolvent always. Okay, so please remember this. It's a very good question. I'm glad. Please ask questions like this because these are extremely important for the understanding. Nothing here is easy, but it's also a very important theory for the understanding of a Many-Fermion correlation problem. Well, then we have to go to third order. So I guess what is then third order? Okay, let's see how much of it I can discuss. Okay, so in third order you have R0W cube acting on phi0. That's the principal term. And then we have the renormalization term actually here. So I guess there is some hope that something will be cancelled out if there is the renormalization term. Okay, it's phi0 R phi0 W R0 W phi0, which is, as you remember, the second order correction to the energy, times R0 squared W phi0, okay? That's what our bracketing technique will tell us in this case. All right. Again, I'll focus on terms originating from V, okay? Because, I wouldn't really gain a lot of new information by doing the Q terms, okay? Q containing terms, okay? All right, well, let's see what skeletons are here. Okay? Maybe I'll continue. So we have 3D vertices. Okay? Maybe I'll put them this way. All right? I can call them 1, 2, 3. You can start by simply drawing diagrams which are completely disconnected, where each V vertex is disconnected, right? Has its own piece. Is its own piece. Okay. All right. Very good now. And denominator resolvents go this way. Okay. All right. Well then, we can start looking at diagrams which are disconnected, but where two of the three pieces are connected, forming a connected piece. Okay. That's the next category. Maybe I'll put some sort of line here, splitting it up. Okay. So I'm going to connect 1 and 2. Okay. So I will connect 1 and 2, but I'll keep the third one separate from it. Okay. So we can connect 1 and 2 with one line, keeping the third one there. Okay. I can connect 1 and 2 with two lines, keeping the third diagram separate. Sorry, the third vertex separate, and I can connect 1 and 2 with three lines, and then keeping the third vertex disconnected from it. And I can do one more thing. That is, okay. So maybe I'll also put resolvents here. I'm always doing this. They're all on, okay. And then we'll have the situation where we connect 1 and 2 completely. Okay, and then we have V. That's also allowed because, you know, the dangerous denominators are avoided, right? We have external lines, we have lines in the middle here. Okay, so everything is fine. Okay, so we have those. Well then, let's look at cases where we're connecting 1 and 3. Okay? If you look at 1 and 3, okay, I'm using this notation, 1, 2, 3, okay? Well, I have to connect this one and that one, and keep this one disconnected from the other two, okay? So you end up with the following. You can connect 1 and 3 with one line, okay? This is 1, this is 3, where is 2? 2 is between 1 and 3, so it's sitting here, okay? Is this clear to everybody? That's how I set it up. Then we'll have 1 and 3 connected with two lines. And you can have 1 and 3 connected with three lines. And 2 is somewhere in the middle. And you can connect 1 and 3 with four lines. You can do even that. Okay? Is this clear? And again, if you want to be sort of picky about it, you can put resolvents. But that's not true. I mean, we know how to do it, so. Okay, obvious. All right? So then we have the next case. Maybe I'll go to the next blackboard. On the left. Okay? Maybe we'll go back here. In this a little bit. And then there will be a case where you connect 2 and 3. Okay? So now connect 2 and 3. Vertices 2 and 3. Leave vertex 1. Isolated from those other two. So we can connect 2 and 3 with one line. You can see lots of logic in this, right? Well, where is the 3? This is 2. This is 3. Where is 3? Where is 1? 1 is in front. It's over here. That's the ordering of vertices that you have to come up with. Okay? Well, then I can connect 2 and 3 with two lines, putting the one in front of them, and then I can connect. Why am I doing this? Okay, 3 lines here, and there is something interesting now. I can try to do one more. But, before I was connecting 2 with 4 lines as well. Why don't we try it? Okay. So this is 2 and 3. Where is 1 then? 1 is in front of it, over here. Is this okay? No. You see? We are violating now the dangerous denominator rule. That is gone. That's like drawing this is a huge fine, let's say $10,000 or something, right? You're stopped on by the policeman. I think that's what he should do if he asks you a question about this diagram. Okay? Or she. All right. So we're learning that this case is a little bit different. Then, of course, we exhausted now all possibilities forming disconnected diagrams containing 3 pieces of 2. Well, then the next thing is to do connected diagrams. Okay? Well, what are the connected diagrams? I'm not going to draw all of them now because we've already learned they're not cancelling out. So we're not going to be really spending a lot of time on something that doesn't go away. But let's just start. Let me give you sort of an example. Okay, you know, you can start with a connected diagram that has a maximum number of external lines. So my suggestion is organize them in this way. Start with a maximum number of external lines and then go down. Okay, connecting more and more lines. So you know, it would be something like this. Okay, you agree that that's connected. Okay, and you can see it has the largest number of lines you can have in a connected diagram. You know, and then of course you can form various permutations of vertices. You can think of this by simply dragging this middle vertex. You know, these two are sort of the same, similar vertices. They have 3 external lines, each one of them. This one seems different. So, you know, you can drag this one in different ways to obtain other variants. Okay? So the next variant would be, take it, put it in the bed. Okay? Something like this. All right? So you see, so I have now 1, 2, 3. This is 1, 3, 2, right? So I drag that to the rear seat, right? And then I can also put it in front. Here it's in the middle between the other two. So in front you can have it this way, and then, you know, let's say this way, and then maybe that way. Okay, that's another permutation. There are no other actual diagrams here in this category. Then of course you would have other diagrams. So, you know, connected diagrams. I'll just say etc. Okay? There are a huge number of them. Okay? Please note that these connected diagrams are characterized by having, there are time versions of the second kind actually. Because if I put an arrow, say, going this way, so maybe, let's say, if I drag it this way. Yeah, so suppose I put an arrow, imagine for a second, if I do this, what's going to happen to this line? If I drag this vertex there, it's going to go this way. Okay? That means that connected diagrams can be organized among themselves as time versions of the second kind. What should I call them then? The second TV channel, TV2. Okay? Time versions of the second kind. But if you look at the, okay, so that's what happens to connected diagrams. And as I said, there are many of them that can group in this way. But when you look at the disconnected diagrams, they are related to themselves by time versions of the first kind. Okay? Let's look at this. For example, let me pick up an example. Suppose I pick up this. Okay? Think about for a second about this diagram. Let's find it. So this is when I did 1 and 2, right? What about 1 and 3? Well, you have it here. That's a time version of it. But that time version doesn't change the orientation of lines. If, say, the middle lines, the connected lines were particles, they will remain particles when you start permuting vertices. Can you see this? This is very important that you see this because, that's going to be very critical for the reconstruction. Okay? So I have 3 versions here, okay, that look similar topologically in terms of how lines are connected and so on, but they are time versions of the first kind. So there's something interesting here. Connected diagrams are organized in groups of time versions of the second kind, but the disconnected ones simply be organized according to the time versions of the first kind. Okay? Well, we're going to take advantage of that. And actually, if you think logically about it, those are all 3 possibilities. You cannot form the 4th copy of this by just permuting vertices. If you produce a 4th copy, it's going to be equivalent to the other that you already have. Okay? So it seems like we can group disconnected diagrams using time versions of the first kind. But I would like you to, I have to stop now. Maybe you can tell me, okay, let's see if I, do we have anything there? No. Okay. Okay, Nicole, so I would like now to have a picture of all diagrams. I would like students now to see, if it's something we can leave the room in a moment. Do you see something that you haven't seen before in terms of the kinds of diagrams we see there. You certainly see connected diagrams, and we see disconnected diagrams. They're all coming from the principal order there. Okay? So that's similar to the previous orders. But do you see something here, some kind of a diagram, a type of a diagram, I should say, that we haven't seen before? And you don't need to know. Look, this is a hard question. But I'm just wondering if you see something kind of new, surprising, or whatever. Because it can also help us. And if you have, maybe you can see from, with your camera, you can zoom these things, you can see
These
them.
are just an expectation value when you operate that way.
Perfect. How did you know that? Just Charles. Or some more.
And then a process of elimination.
Fantastic. Fantastic. You see, we have something new we haven't seen before. We have a disconnected diagram here. And there should be, where is it? Let's see. This is 1 and 3. I think I have to go back here, right? This one. We have two diagrams here that are disconnected, but they differ from all other disconnected diagrams by having a piece inside which is fully connected. We call such pieces, connected pieces inside disconnected diagrams, vacuum pieces. Vacuum piece because it sort of formally represents the expectation value. Okay? If you think about it, no external lines. Those two are examples of the so-called unlinked diagrams. Okay? So now you can see we have another term that we need to worry about. Okay? We have diagrams here which are disconnected and which contain vacuum pieces. In our case, there's one. By definition, an unlinked diagram is a diagram, disconnected diagram. By definition, an unlinked diagram is a disconnected diagram that contains at least one, can have more, at least one vacuum piece. Okay? On the same token, what is in the linked diagram? You just have to negate it. A linked diagram is a connected or disconnected diagram that does not contain vacuum pieces. Okay? So, I have to stop here. We'll start the next lecture from this point, okay? What I'll do next time, I'll simply start by saying, look, we discovered something fundamentally important here. Among various diagrams that we have, we found connected diagrams. That's the easy part. That's an easy part for us now. We found disconnected but linked diagrams. For example, this is disconnected but linked because there is no vacuum piece in it. And we found also disconnected diagrams which are unlinked because Cole found out them for us in this big mess on the blackboards. Okay? And I'll show you that it is the unlinked diagrams of the wave function that eliminate renormalization terms. And that's the linked cluster here. Okay? I guess that's going to be a good beginning of Wednesday lecture. Okay, so thank you very much, and see you on Wednesday.